We are Western Michigan University's Advanced Rocketry Club. Here we'll discuss the 2019-2020 Argonia Cup Challenge launch vehicle and mission system designs. We will introduce the teams and discuss their designs. First, we will introduce the launch vehicle team members.
I'm Rachel Cabin, second year in aerospace engineering.
I'm Alexis Lind. I'm a second year in aerospace engineering.
I'm Lauren Dickinson, and I'm a sophomore in aerospace engineering.
My name is Ryan Dool, and I'm a freshman in aerospace engineering.
My name is Ethan Silverman. I'm a sophomore in aerospace engineering.
I'm Nathan Keeterman, a senior in aerospace engineering.
The launch vehicle is a modified DX-3 Massive, a 5.5-inch diameter fiberglass airframe with 3 trapezoidal fiberglass fins. Modifications have been made to the lower and upper airframe section length to increase launch vehicle stability when loaded with the payload and mission systems. The 5.5-inch diameter was chosen to best accommodate the design payload systems, as the ability to reliably deliver the golf ball is of the highest priority to the team. Here we have an open rocket modeling of the launch vehicle. The black square at the nose cone shoulder represents the location of the mission systems prior to deployment. Upon apogee, the upper ejection charge will eject the nose cone while remaining tethered, eject the drogue parachute, and the mission systems. The mission system will passively descend, and the launch vehicle will descend under drogue until 500 feet, where the lower deployment charge will eject the main parachute. The passive descent of the mission systems will be further discussed in the mission system sections. This model has accurate balancing of payload, mission systems, recovery hardware, and ballasting weight. Here you can see early construction progress of the launch vehicle, and in the foreground are subscale testbed with alternate FIG configurations. Flight simulations and modeling have yielded the following predicted flight data. An apogee of 8,130 feet is predicted. While this is very close to the 8,000 feet minimum apogee, flight tests of the testbed and experience with the Pegasus 1 rocket has shown this method to regularly underpredict the apogee. Therefore, the team is confident in its ability to reach the 8,000 feet minimum apogee. One data point worth mentioning is the 2.13 calibers of stability upon launch rail exit, exhibiting the very safe nature of the launch vehicle. This was a large design priority of the team. Using Monte Carlo simulation methods, flight simulations were used to predict potential flight behaviors. Here we have one such flight simulation. In this specific simulation, the lateral drift distance of the launch vehicle is less than 600 feet, which is indicative of the many other simulations. This is an important quality of the launch vehicle, as minimizing drift distance will decrease the distance needed to be covered by the mission systems, assuming the target is in the direction of the launch site. The simulations were conducted under the power of an Aerotech L2200 motor. Shown here is the thrust curve data. The L2200 was chosen as it was one of the only motors to lift the launch vehicle to the required 8,000 feet apogee and was within total impulse requirements of the competition.
Hi, my name is Chase Ragland. I'm the 2019-2020 ARC Mission Team Lead, and I'd like to introduce you to my team.
Hi, my name is Nate Owen, and I'm a sophomore in aerospace engineering.
Hi, I'm Matthias Stremler, and I'm a senior in aerospace engineering.
Hi, my name's Aiden, and I'm a junior studying aerospace engineering.
Hi, my name's Ethan Reed, and I'm a junior studying aerospace engineering.
My name is Scott Miller, and I'm a junior studying aerospace engineering.
Hello, my name is Amir Laura, and I'm a junior in aerospace engineering.
ARC's solution to the Argonia Cup Challenge is a folding quadcopter. This quadcopter will be deployed at apogee. It will passively fall to 500 feet, where autonomous flight controls will take over, guiding the payload to the target location.
Hi, we're members of the mission team, and we primarily focused on the passive drag surfaces.
The design of these drag surfaces is to maintain vertical orientation on the way down from apogee. It will keep the speed of the payload below the terminal velocity required, and it will provide roll stability using these vertical strips here.
So using our targeted descent velocity in order to minimize lateral drift, as well as the coefficient of drag of a flat plate, and our mass of the drone, we were able to calculate the required area to maintain those conditions, and then using that area, we calculated the required thickness of the strips relative to the radial direction.
The material chosen for these drag surfaces is ripstop nylon. It is very durable, and the team has plenty of experience using it on other projects.
Once we reach apogee, the staging sequence will initiate ejecting the drone from the launch vehicle, and then the air will catch the passive drag surfaces, deploying the booms, and they will remain deployed during the descent.
We're members of the mission team, and we have primarily focused on designing the drone body.
The main objective of the drone body is to safely take down the golf ball during its descent while being below terminal velocity. There are 5 critical features I'd like to highlight. First, The shape of our first iteration was to allow for a better aerodynamic performance. The slot at the top is to allow for the battery and provide additional structural integrity. The area on the top to allow for the flight controller. The area where we would house the golf ball using an adhesive. And finally, we would have grooves along the sides to allow for the foldable booms. Also a side note that we would employ a passive drag system between the booms.
In our final iteration, the same 5 critical features were designed for, including the flight controller on top, as well as having room on the inside of our profile to house the battery, the golf ball, and the avionics, as well as the drag surface area. This final design includes a larger room to house the drag surface area, a much lighter weight, and the capability to be 3D printed. This final design has also completed successfully a 20G acceleration stress test.
To select the proper combination of propellers, motors, controller, and battery, a calculation website was used called eCalc. This site allowed for parameters to be set such as weight, battery amp hours, and other general aspects of the quadcopter, and the website would return estimated weight, flight time, and other data with that configuration. For our purposes, we were trying to minimize weight and maximize flight time, so we decided on using a 5,000 milliamp hour battery with Emax 820 kV motors. Continuing with hardware, the flight controller will be a Raspberry Pi with a Navio 2 hat that will be running ArduPilot. The Navio hat has orientation sensors such as accelerometers and gyroscopes that are used for orientation control and motion sensing. The board has radio interfaces that will be used to communicate with the ground station. On board is also a GPS system that will allow ArduPilot to autonomously fly the drone to the landing site.